Oh, what a day! What a lovely day!
Welcome to, oh, my camera's definitely frozen, to Flat Earth Debate Live. I'm your host, Nathan Oakley, and if you're new to this channel, or you've not done so already, then be sure to subscribe, hit the bell notification icon and join button to keep up to date with the Flat Earth Debate. If you'd like to support the channel, there is a super chat that runs alongside each of these shows while they are live. There's also a PayPal, Patreon, and crypto link in the info box below the video. Most importantly, if you'd like to join the discussion, simply mute the page you are currently watching, then click the link in the info box below, I can't see me, this video, to join the panel and express your views on the nature of Earth. If you do join, please don't swear. If you do, you'll be ejected, and if you are, please don't try to rejoin the stream using sock accounts. You'll be warmly welcome back on the next stream. Please also share the show on social media. Sharing the show obviously increases the live audience, but this in turn increases the chances of a more diverse panel. So please share the show on Facebook and Twitter. And one last time, if you're new to the channel or you've not done so already, then be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth Debate. See if I can actually get the other camera working before I use the panel. Does that work? That's the backup camera. Hey ho, technical issues. We are joined by Righteous Force. I don't know who's got the... is that Bev? And Chocolate Sane and 10th Man in G+, together with a whole bunch of people in Discord. So, welcome one and all.
Good morning.
Hello, hello.
Terrible intro.
Good morning, Vietnam.
Worst start to the show ever. Cameras froze, and I'm like, oh god, where's the backup camera? I can't find it because it's been months since I've used it. But hey ho, let's do a bit of housekeeping. Who is it? Is it Bev? Was all right? Yes, it is.
Yes.
Hey Bev.
Yeah. Hey.
Are you on Master B now? Has somebody added you?
No, not as far as I'm aware. No.
Oh,
No, I just sent him the link.
Can you add him to Master B? Do you know how to do that? Should be doing
No,
this
I
in the
don't.
pre-show, really. But hey, let's do housekeeping before we get into endless admin. Any evidence of a physical Earth curve?
No,
Only in the globe reification model.
No? No signs of Earth curve at all?
no.
Absolutely zero here.
Any evidence of axial rotation of the Earth-based variety?
No, I don't think so. Just in the books, pictures.
Any scientific evidence of gravity?
What is it?
Only in the reified globe reification model.
Get some repetitive answers, it seems, today. Any evidence of the distance to the sun?
It's over there.
Oh, it's not here. It's late. Any evidence of a self-perpetuating molten iron core at the centre of a presupposed spherical Earth?
That's a good one.
That is even
no.
possible.
That's a negative, Ghost Rider.
Any evidence of the R value, Earth radius?
R
That's
value.
been smashed.
There. There it goes.
No. Because at best, what has happened is the R value has been debunked. At best, of course.
Any single viable hypothesis from any of the fields of astronomy, cosmology, or astrophysics?
I don't think they qualify for scientific evidence in those fields.
I'd agree. I think that's it. That concludes the housekeeping.
No, curvature.
Gas
Forgot
pressure.
curvature. Gas pressure, curvature.
Oh, gas pressure. No, I did curvature, both of them first. So, any evidence you can have gas pressure without the necessary antecedent of a container to press upon?
I have something on that.
Cool. Good round out to the housekeeping. Go ahead.
I'm an instrument tech, I work with pressures all the time. And one of the things I've noticed in this debate is the Globers are quick to confuse differential pressure with vacuum. But there's actually three different kinds of pressure. There's absolute pressure, differential pressure, and atmospheric pressure. And if you don't pay attention, they'll do like a cup trick with it.
So go on then. You explain the bait and switch that they use.
Well, they'll say vacuum and then describe that as a differential pressure. But when we're talking about vacuum, we're talking about absolute. That's all the way to zero.
I see.
Yeah, I've heard that nonsense. Zanuck has said things like, "Oh, a pressure differential would be a vacuum. So if the pressure is different at your feet than at the top of your head, that's a vacuum because you've got a pressure differential." It's
Yeah,
ridiculous.
he's doing a bait and switch with you. He is actually not addressing the point. He's talking about something else.
Oh, I know. It's the same thing like when he says with the wings. Oh, you got a pressure differential above the wing and below the wing. When our question is, how do we have the pressure at all? But he wants to say, oh, that's that. There you go. That's evidence of a vacuum without a container because you have differential pressure. It's just another way to try to sneak in their nonsense and hope that people aren't paying attention. So yeah, you're absolutely right, man.
Yeah, quantum
Not
race.
only, hang on, not only Zanuck, but Dr. Danny Faulkner said an airplane wing at 30,000 feet has less pressure above it than below it. So there's your vacuum. So it's not just
Funny thing
limited
is,
to
I
Zanuck.
heard Zanuck with that first before Danny. Danny tried that old banana in the tailpipe first, so Danny was late with that
I
crap.
concur. I con- I
Yep.
concur. Zanuck was the first to say it for my ears to hear as well. But I don't know when Danny came up with it.
Well, the next time they
Well,
try
I
that
mean,
shell
he
game
probably
with
got
you,
it
that's all
from
you have to
Zanuck,
say.
which wouldn't surprise me because he did get his little vacuum without a container video from who was it? Hillbilly, Mr. PhD over there. That's who you cite, Hillbilly Blue Balls, for your vacuum without a container.
Yeah, but I thought
Meanwhile, you
he
have two
said
containers.
I thought he said you shouldn't go to YouTube videos for your sources.
Ah, that would mean if it's like one of those do as I say, not as I do.
Well, that's incomplete. So he didn't say, look, you shouldn't go to Google. He said you should go to him. So he can go to Google.
Yep.
Right.
What's up, Arvin?
So to summarise the argument, we ask how you can have gas pressure. That would be X in this instance. X is gas pressure for this argument. How can you have X, that would be gas pressure, without something to press upon, a container? Gas pressure is, by definition, the force exerted on the walls of its container. That is gas pressure. How can you have gas pressure without the necessary antecedent of containment to press upon? They address this argument by saying, we can have delta X, that would be gas pressure gradients. And then they address how they have gas pressure gradients, a delta of gas pressure. So when they describe an airplane wing and the differential in pressure it creates with the Bernoulli effect, we would immediately say, how did you have the gas pressure in the first instance to push an airplane wing through to create a differential? How did you have gas pressure in the first place? If you're claiming we don't have a container and that the sky is in fact a vast void the gas we breathe could fill. Gas wants to fill the available volume it has to fill. That's what gas does by its nature. Fills the available volume. Go speak to MIT about entropy. That's what gas does. It's gas behaviour. So gas wants to expand at high speed in all directions, and it's claimed, if you're a heliocentric religion believer, then it's claimed the sky's a vacuum. Outer space is a sky vacuum. Well, the gas we're breathing would want to fill that space. It would want to expand in all directions to fill the available volume. Hence the question, if the sky is a vacuum, how can we have gas pressure without a container? the gas we're breathing would fill the space. Well, they don't address that question. They address how you have a differential in gas pressure, not addressing how we'd have gas pressure in the first instance. It's just a red herring.
Exactly, and they do that by the 3 different types of pressures used by.
You're cutting out again.
The way that they do it is engineering. We use 3 different types of pressure, and they substitute the one we're asking about, which is absolute pressure, for differential pressure.
Right. How can you have absolute pressure without a container? Well, once we've got pressure, absolute pressure, we can create a differential within that pressure, and we're going to talk all about that. That's what they do.
Yeah, absolute pressure goes to 0. Differential pressure only deals from atmospheric up.
I see. Atmospheric being atmo, air, and sphere, fundamentalist religious belief. I noticed.
Yeah, I just thought that was interesting how they did that little shell game.
Sure. Most of the arguments for a globe Earth are a shell game. Bait and switch. What's it called? Follow the lady.
You forget there's that other little sneaky one they try to do, which say gas pressure is different from atmospheric pressure.
Yeah.
Just funny, because what's the atmosphere made out of again?
Atmo.
What's atmo?
Air.
Check.
That would be gas,
Can you hear me?
We hear you, Babs.
What up, Babs?
Yeah.
Can I get?
Morning,
Hey,
guys.
Owen. Hey.
Are we still doing housekeeping?
We're kind of doing it. We're on the last question. Hey, Arwin.
Hey, can I have a little special type of ball or a bottle? To the.
You have a what? Sorry, I was
gas
coughing. Say again, Arwin.
Can I have a special ball or a bottle?
A special ball or rebuttal. Yeah, do you want a little drum roll? Dun, 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 dun. Go ahead, Arwin.
Okay. At most, you've disproven gas pressure without a container. See it?
At most.
At most.
Oh, got it. That took me a while. Chocolate's on the ball, thank God.
I got it.
Any more, Arwin? Because I think Babs has got something to say.
No, that was it.
Good joke, though. Very good.
Thank you.
Babs?
Yeah, I do have something that I want to say, and I wanted to present this to you guys last week, but I was kind of busy, and it was also pretty busy on the show. Like, the Discord was packed, and didn't really get an opportunity to jump in and share with you guys this new findings. So I'm going to get Righteous Force to share some images on the screen.
All right, you're presented.
Okay, good.
Well, I'm not
just
sure
looking
if
at the
Nathan has it, but
YouTube page right now, so I might be a little bit delayed. Right, so Hillbilly Blue Balls, also known as Billy Blue Balls, made this video last week. And undoubtedly, this was a response to the discussion that you and I had about perspective and how it relates to Polaris and angular size change and how we can apply it to flat Earth and observations. So what Hilly Blue Balls chose to do in this video was to use these blocks. They look like Jenga blocks, and they're all arranged equally spaced away from each other, and they're all the same size. And basically, what he's trying to show us here is that perspective is a real thing, but as far as the globe Earth arguments are concerned, they don't use perspective to represent obstruction, because they prefer using orthographic view, because in orthographic view you're able to show everything pretty much from a side view. You're able to represent like all the objects that are being observed, or all the objects that are in question. And in perspective view, you don't really get the opportunity to do that. So if you could go to the next image. Perfect. So the argument that he was making here is that the only time where we see perspective, which is things getting smaller the further away they are from us, in relationship to our observation or viewing point, the only time perspective is a factor is when the objects are different distances away from each other. But as you can see here in this example, we don't see perspective from a side-on view because these objects are equally distanced away from us. They're all at the same distance away from us. That's why we don't see that effect. And could you go to the next image, Righteous? Right, so further demonstrating that point here that we only see perspective when we're observing objects that are moving further away from us. But if they're equally distanced away from us, we don't see this effect. Next image, please. Right, and we see this here with these fence posts. As the fence posts move away from us, their sizes change. And these measurements can either be angular size or apparent size, just depending on how you choose to measure these. But the fact still remains that objects that are moving away from us are changing in size. They're reducing in size. Okay, next image, please.
Reducing in apparent size.
Correct. They're not actually reducing in size, but their apparent size is reducing. Okay. So as you can see here with the two images juxtaposed alongside each other, the fence posts remain the same size as long as we view them from equal distances. It's only when we view them from different distances that we start to see this perspective effect. Next image, please. Okay, so this change in apparent size isn't necessarily constant. It changes based on your location and your elevation. So the higher up you go will affect the rate of size change. So what I was trying to do was trying to get like a fixed rate to sort of calibrate how these objects are changing in size the further away they move from us. But one thing I realized is that there's no fixed rate as far as perspective is concerned. All that we can say for sure is that things that are moving away from us are always going to be reducing in size. Next image.
One minor correction. When you're saying rate, you mean angle. The angle that you're taking these images from is what will determine that. So
exactly, the angle, yeah. The angle that you're viewing these images from is what's going to determine the rate. If that makes sense.
Yeah, you're using the word rate, you mean angle. Perfect. Next slide.
I mean angle, correct. Okay, next image.
This is the next image.
Next one, sorry. So as far as how we can apply these measurements to what we're looking at, as far as the images that we're viewing, there are different calibrations of measurement that we can use to measure these. Since we're looking at photographs, we can either measure pixels, inches, centimeters, millimeters, points, picas, or columns. But it doesn't really matter what scale you choose to measure these objects. The fact still remains that the further away objects move from us, they change in size. Doesn't matter what unit of measurement is being used, that fact still remains. Next image. Okay, so I've presented this before, and I feel like it's a good representation to help people understand how perspective is applied as far as flat Earth and observations pertaining to flat Earth are concerned. So in reality, we know that anything that's below our eye level can't obstruct things that are above our eye level. And I'm using this red line in this image to represent our eye level. And I'm going to demonstrate to you how obstruction can work as a result of apparent size change and perspective. Next image, please. Okay, so we can see that the ground appears to rise up and get closer to our eye level as a result of perspective. Now, in actuality, the ground is not rising up. This is just an effect that is the result of our eyesight. Our eyesight tends to make things converge to a point. The further away in the distance, whatever it is we're looking at is. So this is something that isn't taken into consideration in orthographic view. When we're looking at things in side view, we can't really represent this apparent rising of the ground and this apparent stooping of the ceiling. These two things can't be represented in orthographic view, and this is why this is important in terms of the observations that we're looking at. We need to represent what is actually taking place in reality. Next image, please. Okay, so on the sides here, we can see that there is this shrinking or this apparent angular size change that happens the further away we look in the distance. This is also something that isn't represented in orthographic view. And this is also something that can affect how much things are obstructed when we're observing objects in the distance. Next image, please. Okay, so here we have an object in the distance, and about 3/4 of this object is below our eye level, and 1/4 of it is above our eye level. Now, what I'm going to demonstrate to you is if we have an object that is the exact same size as what we're looking at in the distance, if it's closer to us, it's going to be larger in angular size than what is further away from us. And the result of this is that something that's shrunken or reduced in apparent or angular size as it moves further away from us can be obstructed by something that is closer to us and is larger, as long as it is all below our eye level. So next image, please. So you can see that this object here is being obstructed by another object that is the exact same size. The factors to keep in mind here are that the size, the difference in angular size is what is resulting in this obstruction. Next image, please. Okay, so here we have the typical images that are presented to us by the globe earthers. They show us an image in a side-on view and ask us, why is this being obstructed? We should be able to see it. And they neglect representing angular size change. They also neglect representing the effects that we discussed prior to this, which is the ground appears to rise up or get closer to your eye level the further away you're observing objects in the distance. Now, this is not represented at all in this image, and it gives the misguided idea that this is what you would expect to see on a flat Earth. But realistically, this is not how our eyes work. This is not what we see in reality. So telling people that this is how flat Earth should work, and this is, you know, how things should be represented on our model is false and incorrect. Next image, please. Okay, so here we have a hydrostatic leveling rig. And this is a tool that you can use to measure the horizon in relationship to your eye level. And we can see that at sea level, the horizon is actually at our eye level. Now, why is this important? This is important because majority of these observations that we're doing are at sea level. So we're looking at things that are at our eye level. And what we should apply is that rule that anything that is below our eye level can't obstruct anything that is above our eye level. So we notice that in most of these observations, all of the obstruction is taking place below our eye level. Now, what we need to do is apply angular size and start looking at how what is obstructing these objects in the distance is actually doing. For example, if we have waves that are closer to us in the foreground, if they're larger in angular size, is there a possibility that they could obstruct something that is further away, something that's reduced in size, just like those two objects that I showed you previously? One was smaller than the other, and that resulted in obstruction. Okay, next image, please. Okay, so as we increase our elevation, we notice the horizon drop. This is this is one of the ways that the Globers are able to reificate their model by saying that we observe horizon drop, therefore we're on a curved surface. And they completely ignore atmospheric effects. Not until recently, when they admitted that the horizon is apparent, it's always subject to refraction. So keep this in mind whenever they want to mention that the horizon is dropping as a result of curvature, when in actuality the horizon doesn't have a fixed location. It's either closer to us or further away from us based on atmospheric effects, not as a result of Earth's geometry. Next image, please. Okay, as you can see here, further up we go, the horizon gets lower from our eye level. Why this is happening? I believe it is a result of atmospheric refraction and not Earth curve. Next image, please. Now, how this relates to everything that we've been discussing thus far, as far as the black swan is concerned, is that we've heard the Globers state that looming is what causes us to see further than what we would normally see on a geometric globe model. But in reality, we never see looming. Looming isn't a real effect. As far as I know, what we're seeing is inferior mirages. We're seeing boats that are being inferior miraged, and people are asserting that that effect that we're viewing is actually looming, when in actuality it's not. It's inferior mirage.
Could you make a minor correction? So in the case of looming, what you would have is an inferior mirage of the sky below the boat. The boat's still in the same position it always would be, but the inferior mirage isn't the boat, it's the sky.
It's the sky, exactly. It is the sky that is being inferior miraged, creating the illusion that the boat is floating, when in actuality it isn't. It's just the sky that is being refracted. Next image, please. Okay, so this is how the looming effect works. We know that light tends to bend towards a denser medium, and cold air tends to be denser than warm air. So in order for this effect to work, what would be required would be a colder layer of air above the warm layer, which would result in the light bending downwards. Actually, sorry, I got that backwards. What would be required for the looming effect would be a colder layer of air below a warm layer of air. So therefore, the light would bend towards a denser medium, which is the cold air, and it would bend in a downwards direction, which would cause what we're looking at to be loomed upwards.
I'm just going to bring some clarity to that. I'm sorry, because that was just slightly convoluted. I'm really sorry to add to your presentation. So if you can't tell already, this is a Muppet Vision representation. Therefore, this will be the Glober's description of what looming would be in their representation, side on with you seeing your own head. Not that we see that in photographs. Nevertheless, what's just been described is how they describe the boat being raised up and the effect that would be needed for their argument for that to happen. So this is a devil's advocate from the Globe side, what they say about looming and what would be necessitated for that to happen. Hope that's clear.
Exactly. Yeah, just to make it clear, this is all on the Globe model. So if we could go to the next image, please. Right, so this is a demonstration of the inferior mirage effect. Here we see the boat appearing to hover or levitate above the water, but in actuality that's not what's really happening. The sky is just being inferior miraged below the boat, creating this effect. And I think this is what the Globers think looming is, but it really isn't. Because do you really think this is a hologram of the actual boat being loomed up behind Earth curve? That seems
again. I'm really sorry. I'm really sorry. This is what they think their version of looming is. So based on the explanation just given about the boat being raised up, they, the globe heads, would assert that this is the true horizon, the geometric Earth curve edge shown in their model, marked with an X and labelled horizon. That's what they would say this is. And on first inspection, that seemed fairly obvious, right? It's the hard line. Therefore, that is the horizon, right? Well, no. If you use off-center vision, you can see that the horizon is precisely where it would be on any other day. And so is the boat. In other words, if you came back when you didn't have an inferior mirage of the sky below the horizon, so that's where your mirage comes from. This is an actual description of what's actually occurring, as opposed to the demonstration that was on 2 slides ago, where you've got your eyeball looking up from the left. Well, as you can probably tell, we don't see the side of our own head in this picture. That's the first problem with their depiction, and the light bending the wrong way round based on how the actual heat of the temperature in the air and the water would be means that their explanation is nonsense. The point is that what we actually have is a horizon behind the boat slightly, because it's quite close to the photographer. It's not a black swan necessarily. Anyway, the sky is then mirage below the boat, giving you a false horizon, which is this line here. The true horizon, if you want to call it that, would be slightly behind the boat. And if you use off-center vision, you don't even have to adjust the contrast. You can see exactly where that line is.
Yeah, correct. Exactly. Next image, please. Okay, lastly, I wanted to show this as a demonstration of how we only see obstruction below our eye level. As you can see here, everything that is obstructed in this image is below our eye level. And I am yet to see obstruction taking place above our eye level. It is possible to obstruct something above our eye level, but it can only be obstructed with something that is actually above our eye level. So from what we can extrapolate from this is that the water is below our eye level, and it's closer to us than this boat actually is. Therefore, obstruction can take place. Conversely, other things can lead to this effect. for one, we know that we are in an atmosphere that does cause refraction. And we know that just as we discussed before, light tends to bend towards the denser medium. So if we have a colder layer of air above a warmer layer of air, for example, if there's a warm layer of air on the surface of this water, and just above it is a colder layer of air, that light that is traveling is gonna bend towards the denser medium or the colder air, causing what we're looking at to sink downwards. So this could be sinking refraction as well. So there are several things that could lead to this other than just Earth curvature. But as far as the globers are concerned, it is only Earth curvature that can result in this type of effect. All right, over.
Is that the end of your presentation?
Yep.
Very good. Excellent. So for the audience's benefit, I've just put my 3D'ized version of Muppet Vision on. I did pop it up a couple of times during your presentation. In terms of how we would actually view this, we'd get the view through this box. But as with Muppet Vision, we're seeing the actual box representative of the viewfinder in the camera. So we're seeing the side of our own head represented by this box. You wouldn't see this, you'd only see what's presented in this picture. Now, what would be presented in this picture if this mountain was a mountain and right next to you would be a gystonking enormous mountain in the foreground. These mountains here would be massive because they're right next to you. However, these mountains here are considerably further away and would be teeny tiny. But as you can see in my representation, each and every one presents itself as exactly the same size as the one next to it. So it's a very useful way of removing perspective. I don't know if Righteous Force can go back to the picture of the boat with the guy on the left-hand side, boat on the right. But when you've got a picture that's showing you something close to you in the foreground being exactly the same size as something far away, you know that there's no perspective, otherwise known as apparent sizes, being accounted for. Not that one, the cartoon boat side on Righteous. So when we do this, we can attribute a particular value to each of these mountains. We can give them a whole number value, which would be feet and inches or meters. So I can say that this is 1,000-foot mountain, this is 1,000-foot mountain, this is 1,000-foot mountain, this is 1,000-foot. And it's a couple before, it's a cartoony one that's literally just like a line pencil drawing of a guy with a boat on the right. You'll get there. So in the mathematics for Earth geometry, all of the targets remain the same exact size. And when you get your picture of a guy on the left, target on the right, well, you can write any value you like on this line. I can call this distance 10 meters, or I can call it 1,000,000 kilometers. I can increase the number on this till it fills the entire line, and it won't change the representation of the picture. It doesn't make this any smaller, because if I write 6 foot on this and 30 foot on this, i.e. 6 foot on the man on the left and 30 foot on the boat, and I put 10 million in between in terms of the distance between them, it won't change the representation. But the fact that the boat's completely vanished when you have an actual picture, I don't know if you can put anything that's actual, any photograph on, or I'll find one while you're doing it. Let's just do that. That'll do. So when you've got an actual picture, number one, you don't see the side of your own head. You can't see yourself in the picture. And number two, everything that's further away is going to get smaller. This tree here is obviously much, much bigger in the picture than the trees in the far distance because of perspective. But if you stick it side on, it's very useful for removing that aspect. And you can say that the boat, in the case of this image, that's, I don't know, let's call it a reasonable distance, 20 miles away, has slightly vanished due to angular limitations. And what I mean by angular limitations is where they draw a single line, or in the case of the Earth curve maths, they draw a tangent to their Earth curve edge obstruction physical geometric horizon. But what you've actually got is an angle. You've got an angle to the top of the boat and an angle to the bottom of the boat. Now that angle, if the boat was right in front of you, would be a much wider angle. And the further away you go, the smaller the angle becomes. That would be the apparent size of the boat, not factored in when you put it in Muppet Vision side on. Well, that's how they've removed perspective from the Earth curve maths. They've removed apparent sizes. How do you know? Well, because they'll be giving you the sizes in feet and inches or meters, and those values do not change with distance. Unlike reality, things in reality that are further away are much smaller than things that are much, much closer to you. This tree here isn't necessarily much, much, much bigger than this tree in the distance. It's just a lot closer. Its apparent size is larger. Now, ironically, they're all babbling on at the moment because of the black swan about how the geometric horizon, necessitated in the globe model, is actually, quote-unquote, apparent. Now, number one, all horizons are apparent. It's part of the definition. The apparent position where the sky meets the ground, or the position where the sky appears to meet the ground. The sky doesn't meet the ground. All horizons are apparent. But they introduce this extra horizon with the word apparent because we can't see their physical necessitated geometric horizon that's in their model, marked with an X and labelled horizon. When we can't see it, suddenly it becomes apparent. Totally redundant term. Now, the reason this is interesting for this conversation when we're detailing perspective is apparent would be the mathematics that you would require to include perspective. Apparent sizes. And they don't use them. They're not using angular size, otherwise known as apparent size, representing this boat with two lines to the top and to the bottom from your perspective. You've just got a fixed value, whatever I gave it earlier, I can't remember, 30-foot boat and 6-foot man. And those values will never change. Therefore, it's easy to hijack the effects of things getting smaller into the distance till they disappear, and things will disappear from bottom up with a limited enough angle. I'll give you an analogy in a moment. And they can call that effect of things getting smaller till they disappear Earth curve. Now, as for, to round this out, this excellent presentation, perhaps, to round this out, go on.
Billy Blueballs just commented that I wonder why those fence posts are all the same size. So he clearly still doesn't get it. Yes, the fence posts are still all the same size, but because they're moving away from us or they're further away from us, their apparent size is reducing. Now, this is the reason, they expect us to be able to see Australia from New York, because in Muppet Vision, everything is the same size. Everything is on the same level, and there's no atmosphere. Everything is geometrically represented as what you'd expect it to be with no atmosphere. So they clearly don't understand how this effect works. Regardless of how many times we try and explain it to them, they're just not going to get it.
Indeed. So if I give my analogy for bottom-up obstruction, because that's normally the last nail in the coffin, people say, well, things are disappearing from the bottom up, therefore they must be being physically obstructed by an Earth curve edge currently being denied and called apparent, with this redundant term included in the description of a horizon. Nevertheless, bottom-up obstruction, if I take a brick and place it right in front of me, it's very easy to see it has a very large angle. The apparent size of the brick is quite large if it's close. Now, if I push that brick, singular, out to the distance of 1 mile, there's a good chance that that brick becomes too small to see. The angle to the brick, I don't know if you can go back to the boat, Righteous, with the same cartoony, there we go. So, again, with my boat in front of me, the boat has a very wide, large angle. Whereas, in this case, if we're talking about a brick, you put the same exact thing on the horizon, the brick, once it reaches the horizon, becomes very, very small. So, in the same way as some of the leaves on this tree can't be resolved, a brick on the horizon, if this is a mile, just for analogy, would be too small to see. So a single brick at 1 mile disappears. Now, if I now pile on top of that brick another 20 million bricks in the form of a skyscraper, the angular resolution of the brick at the bottom is still too small to see. But the bricks that have been piled on it have got a wider angle. You've increased the angular resolution of the stuff on top of it. It doesn't alter the fact that at the bottom of that building, the brick that disappeared at a mile has still disappeared. The angle's still too small. It doesn't increase the angle of the bottom brick by building on top of it. Ergo, the brick at the bottom has still disappeared at a distance of a mile. From bottom up, due to an angular limitation. Now, if it was a boat, the boat, analogous to the brick, at a given distance will have the bottom section disappearing through angular limitation, and it will continue to disappear due to angular limitation from the bottom up. Sod all to do with Earth curve, everything to do with perspective.
Exactly. I'm glad that you added that last bit at the end, that it's the result of it's a viewing angle. Like we're not able to see that angle that's below where those bricks are, because what they could say is that if things are reducing in angular size, then they should all reduce uniformly. And they don't understand that the reason that we can't see the bottom of buildings is because of an angular limitation. It isn't just an angular size change.
Correct. So again, with the boat on screen, I can do the same analogy again. So, again, in Muppet Vision, as they like to present it, if I draw my angle to the top and to the bottom of this boat, well, the bottom section of the boat has a very small angle. And as it gets further and further away, that angle will get smaller and smaller. So if the boat was right in the foreground, the angle to the bottom section of the boat is still quite wide to the bottom section. And as the bottom section gets further away, the angle to it is more limited. It's not just one angle for the entirety of the boat. It's made up of infinite angles within whatever resolution that you can see. But the bottom, most acute angle is going to be the one that disappears the first, because it's the most limited. And why is it the most limited? Well, because we've got this line. The ground you're looking over limits your angle of view. Now, above you, you've got an infinite angle. You can see all the way up. But down here, you've got something that's going to limit the angle that you can see things at. And the further away, the more limited the bottom is going to get in terms of angular resolution, therefore disappear first. And that's precisely what we observe because of perspective.
Exactly. Not to mention that things that are also closer to us in the foreground are going to be larger in angular size than things that are further away, which could further lead to obstruction as well.
Right, last but by no means least righteous, if you can go to the very first or second slide, the one with the water levelling. The very first water level thing. So while he's bringing that up, here we go. So in this image, their assertion in Muppet Vision that we had earlier with the guy on the left and the boat on the right, we've got a straight line between target and observer for the ground, and a straight line for the view, what he's seeing, dotted line from his eyes on the left to the boat on the right. Well, in this image, as you can see, and as demonstrated very well by Babs, this is raising up. These two are exactly the same amount of liquid. That's the point of the apparatus. And yet it's raising up. And that's going to continue to happen. If this extended out to the horizon, you'd see all of these raising up, raising up, raising up, raising up, raising up. So not curving down away from you, like in their Muppet Vision representation, or in their bastardization of a flat earth world, just a straight line still in Muppet Vision, where you can see forever. What's happening is it's rising up, while they tell you it's curving down. Well, what does that tell you? Well, it's not earth curve, it's perspective. That's why it's rising up, not falling down.
Exactly. Everything that's on the ground starts to move closer and closer to your eye level the further away it goes, which is not represented in Muppet Vision.
And yet they tell you on the globe that from your position where you stand, everything's falling away from you, down. You're at the top of the sphere for everybody, and from your position looking out towards the horizon, you could draw a tangent line between you and that horizon and work out what's going to be obscured, because everything's falling away from you. You're always looking down at things falling away, curving down. Drop. There is no drop.
Yeah.
Raising up. With perspective.
Isn't it funny? Isn't it funny how horizon drop is only visible with elevation? And what they fail to realize is that if you're looking at the horizon drop, you're looking at it at an angle, at a downward angle, as opposed to a straight line. So you're looking at a further distance. If you consider this to be a triangle, the base of the triangle would be shorter than the sloped side. So with elevation, you're looking through a further distance, which has more atmosphere, therefore leading to more refraction, if that makes sense. So if we're looking through more refraction, the horizon is going to be refracted more than it would be at ground level.
But their assertion when they describe horizon drop, the dip angle, is the assertion that we have a geometric horizon, a physical Earth curve. Now, as you raise in altitude, in case this isn't obvious, you should eventually get to the point where the Earth curves into a round ball that they show you with NASA pictures, quote-unquote pictures. But that's the effect. You go up higher, you see more curve, right? So they assert that that is the effect that you'll measure when you get up high and measure the horizon dip. Well, that assertion comes with the necessity for a physical, geometric Earth curve edge as a horizon. Something that's been relinquished and debunked by the Black Swan. So you can't assert that this is a physical Earth curve obstruction that you're going to measure a tangent line to, especially as they're claiming A, we've got no straight lines to draw, it's all refracted, and B, it's non-physical, according to them. So none of the geometry works in these assertions where they claim that the horizon's dropping. We all know full well the horizon's not a physical actual place, it moves with the bloody weather. So drawing tangent lines to it and asserting that it's a physical edge to their sphere for boats to go over is beyond absurd. Now, to round this off, we as flat earthers, anybody who's watching that's new, get asked quite frequently why our boats aren't going over the edge of a disc flying up through a sky vacuum in the form of a flat earth society reification model that's literally got an edge and boats and the sea falling off it. Well, the reason we have this... I just want to get to my point. The reason this is engineered into the flat earth society narrative is because their weakest part of their argument, heliocentrists on the globe, their very weakest part is their edge. Now, they don't call it an edge. They call it Earth curve. It's going over Earth curve. That's what they say. But it's an edge to their sphere with geometry and physicality that they're all currently relinquishing because it's debunked by the Black Swan. We don't have a physical geometric horizon. And that's why they've got to ask us for our edge. Attack is the best form of defence. Rather than focusing on their edge and the boats going over it, when they say boats go over the curve of the Earth, they ask us about our edge that we don't have and don't reify. It's been foisted upon us. But it's because it's the weakest part of their argument. Sorry, go ahead, Babs.
Yeah. And realistically, things can only go over an edge. It has to be an edge in order for it to cause obstruction. And as far as the high altitude pictures that show Earth's curvature, those are cherry picked. They just cherry pick Dwayne Kellum's footage and take snapshots of when the barrel distortion makes it look convex. They don't show you when it looks concave or when it's all wonky. They only show you the cherry picked images that they want you to see that support their fantasy.
Wow. You got some questions?
Can I ask a question?
No, because Brenda's in the queue. Go ahead, Brenda.
Yeah, I have a question. Could you go back to that line drawing of the boat?
Righteous. Thank you.
Yeah, that one. Okay, now, like you said, you can draw a line. There's actually straight lines going from the person's head to the top of the boat and one going to the bottom of the boat, correct? And that angle is very wide when it's close and very narrow when it's further away, correct?
Who are you addressing the question
are you talking to me?
To anybody that wants to answer, either Nathan or anybody else, right? I'm just wanted to get straight that we're on the same page, right?
I'm sorry, I didn't hear the question.
So Nathan said that with this boat, this side view, this orthographic view of the boat, right, when it's really close to the observer there, the angular size would be very large. and the further away it gets very small. Correct?
No,
Yes, that is correct.
No, that's not correct. No.
But that's what you said.
No, it's not included in your Earth curve calculator. This is a representation that's distorting reality. We don't see the side of our own head. It's representative of your Earth curve maths. So when we're looking at pictures like these, we're talking about Earth curve maths, Muppet vision, not reality. That's not what happens in reality at all. But in your maths, there is no such description of the boat being close with a big angle and boat being far away with a wide angle. It's always represented in feet or meters.
But that's what you said. You said when it's close, the angle of the lines connecting, the
say it a second time. I'll say it a second time. I'll say it a second time. It is not included in your maths. My example was to highlight the missing angular relationships in your maths. So when you say, well, when it's close, it's got a wide angle, what in your maths? No, it hasn't. That was my point. Are you going to whistle past that completely for something spurious that's not relevant to my description of your maths that does not include apparent sizes? That's what I was detailing. Do you want to address that? Because that's what I was focused on.
Well, that's what angular size means.
It's not in your calculator, though, is it? Angular size, Brenda. It's always going to be feet.
Yeah, it is calculated.
No, it's always in feet and meters. It's not angular sizes. You just don't understand how you calculate
What
works.
other size? It could be in inches. It could be
no,
in millimeters and meters.
Inches isn't angles. Inches doesn't change with distance. Don't tell me it's got angular size and then say it could be in inches. No, it'd need to be in an angular size.
You don't know what angular size
why are you
is,
laughing?
do you?
Excuse me. Excuse me. Don't tell me with an ad hom what I don't understand. That's an ad hominem attack. So I've got to remove you because you're going to tell me what I do and don't understand. Your maths doesn't include angular sizes, Brenda. For the globe?
Yes, it does.
No, it doesn't. You just said it could use inches.
That's what the feet. Yes, it does.
You're just parroting. Yes, it does. No, you've just said it could use inches. Inches isn't angles.
The size is the angular size is the angle. You can determine.
Why are you telling me what you can determine? It's not in your maths. You use feet and inches, like I've said. Now you're babbling on about what you can determine. I don't care. All you've got in your maths is feet and inches for a target that will not change with distance.
And Nathan,
why are you stuttering and saying my name?
Angle theta.
You don't have angles in the Earth curve maths
to determine the length of the opposite side of the triangle, Nathan.
What's that got to do with the angular size of an object that you're?
That's how you can calculate it.
It's not in the Earth curve maths, though.
Yes, it is. Because
no, it's
if you
not.
know
You're
one
a liar.
side of the triangle and then the angle theta, then you can calculate the other side of the triangle. You mong.
Why are you insulting me and calling me a mong? You do not have angular sizes in the Earth curve mathematics. All targets will be measured in feet and inches or meters and stay those values regardless of their distance. Their angular size will not change. You drawing a sagittar is Earth curve geometry based on Muppet vision with no apparent sizes included.
The apparent size is the size that it appears, and it depends on its distance from you.
And that's not included in the Earth curve maths for about the fifth time.
Yeah, it is.
No, it isn't. Why do you keep spewing this baseless assertion? I've qualified how it isn't there. This boat in the Earth curve maths is always going to be 30 feet. And you're going to tell me how many feet are blocked based on a sagittar you will draw to a physical Earth curve horizon obstruction edge that will block it based on how many feet are missing. Feet which will not change with distance. You'll tell me how many feet and inches are missing from a 30-foot boat. And that's not accounting for angles in any way, shape, or form. You doing geometry and drawing angles from your geometry is not accounting for angular size. You are incorrect or a liar. The Earth curve calculator does not include apparent sizes.
Nathan, is there anything?
Shut up! Don't ask me a question. You're an idiot. With that, I'll say a huge, massive, enormous thank you to all of you who did tune in on the Nathan Oakley 1980 live stream, for hopefully smashing the super chat, liking, commenting, sharing, subscribing. Oh, goddamn camera. Let's go to the backup camera. Liking, commenting, sharing, subscribing, and all that good stuff. Be sure to check out nathanoakley.com and the Flat Earth Debate Forum to keep up to date with the community debate. Stay tuned once again if you're watching on Nathan Oakley Premiering Stream. I'll see you all in the next video.
Oh, what a day! What a lovely day!